Hi, welcome to Sam's Maths Lectures. This is the start of my second lecture on group theory. So last time I introduced the concept of a group, and so now I'm going to give some sort of concrete examples of groups so that they're slightly less abstract. So one of the common groups is the integers under addition, so 0, 1, minus 1, 2, minus 2, and so on. This is obviously a group because addition is associative, 1 plus minus 1 is 0, and whatever. So then we have the integers modulo n, where n is any positive integer. And we indicate the operation as plus bar to sort of indicate that we're taking the modulo at the end. And this is indeed a group. You feel free to check. And then we can also do the non-zero rational numbers under multiplication are a group with identity 1. This includes the negative numbers. We could omit the negative numbers, and that would be fine. But obviously, whatever, it doesn't matter. And we have to omit 0 because 1 over 0 is infinity, and if we define infinity as an element, then we end up with things like infinity is not equal to 3 infinity, which is just a bit strange. Okay, we then have the nth cyclic group, which is quite a common group, where n is any positive integer 1 to whatever. That's the element sort of e, and then some element a, which we then raise to powers, and we basically say that a to the n is equal to e again. So this should maybe be a bar, just to indicate that it's moduloed. Okay. Last time I began with the triangle and its group of symmetries. So that's called the third dihedral group, and then we have the fourth dihedral group is the square, and so on. And so these also have they're non-abelian, so all of these groups up here are abelian, but these ones are not. So if we take, for example, a rotation of 2 pi by 3 radians this way, and a reflection about this axis, if you look where the vertices end up, those two operations do not commute. Okay, we then have the symmetric group Sn, so that's just the permutations of n elements with composition as our thing. And that's also non-abelian for n greater than or equal to 3. Okay. And then we have some groups that are sort of quite large generally. When we work with R or C, they're sort of uncountably infinite, but they're incredibly useful for physics and for other studies of maths, such as manifolds, differential geometry, and Lie groups. Okay. So we take a field f, which is a sort of complex algebraic object that you can think of as being the real complex or rational numbers, because that's usually what it is, and any positive integer n. And then we can just take the n by n square matrices, which are invertible and have entries in f, and that's the general linear group, so GLNF. And then we have sort of several subgroups, which I'll talk about in a second. So the special linear group is those elements which have determinant 1, the orthogonal group, which is those elements whose transpose is their inverse, the special orthogonal group, which is those elements who are orthogonal and special linear, so elements that satisfy this condition but also have a determinant of 1. And then if we have the complex numbers, we have the conjugate transpose A dagger as the inverse, that's the unitary group. And then the special unitary group is the unitary group intersected with the special linear group. And again, this is non-abelian for n greater than or equal to 2. Okay. So first, we have an obvious idea that obviously everything in the special linear group is part of the general linear group, and everything in the special orthogonal group should be part of the special linear group. So what we mean by this, when a group is part of another group, is a subgroup. Okay, so if we have, let G dot be a group, then any subset H, which is a subset of G, that is not empty, so we need H to have some elements, we don't want the empty set to be a group because that's a bit weird, is a subgroup of G dot, and we write that as sort of H less than or equal to G, so not subset like here, but subgroup, and we'll see this notation later. So you might have, for a ring, a subring is written like this, and so on as well. So H is a subgroup if H dot is a group. Okay, so what does that mean? So we already have that dot is associative on H. That sort of trivially follows from the fact that it's associative on G, because every member of H is a member of G. But we need that H has to be closed, so closure. For all f g in H, we have to have that f dot g is in H. Otherwise our subgroup's sort of not really a group, because you can sort of escape from it. Okay. Then you need that the identity is in G, is in H, so the identity of G must belong to H. And then we need inverses, so for all G in H, we must have G inverse is in H. Okay. And so these are sort of three conditions, I guess four if you include non-empty, but we can sort of ignore that one as superfluous. These are equivalent to, so H is less than or equal to G if and only if H is non-empty, and for all f g in H, then we have that f dot g inverse is in H. Okay, so let's prove this. Okay, so obviously H less than or equal to G implies that for all G in H, G inverse is in H by this third condition, and so therefore also f dot G inverse is in H by the closure condition. Okay, so that way is easy. If we go the other way, so H is non-empty, therefore there exists some f in H, so it has an element, but therefore also f dot f inverse is in H by this condition here, and so, but that's just E, the identity, but then we can repeat that again. So therefore EG dot f inverse, which is just f inverse, is in H. So that's sort of our first, that's covered this one and this one. And then finally we have that for all f g in H, G inverse is in H because of this condition, and therefore f dot the inverse of the inverse of G, which is just this condition but with G inverse instead of G, which is f dot G, is in H. Okay, so that's sort of an easier way to check for subgroups. And we can check this for our groups. So first of all, if we take some matrix A, B in the general linear group, GL and F, well, A invertible, B invertible, therefore we have that AB to the minus 1 is just B to the minus 1, A to the minus 1. So we have a closed operation, so that's the first one. Then we have that, there's the identity IN, which is sort of the diagonal matrix 1, 1, dot, dot, dot. Okay, and that is obviously in GL NF because it's its own inverse, so that's the second condition. Then obviously A inverse is in the group because A is invertible, therefore A inverse is invertible because it's just A. So the only thing we have to check is associativity, and so if we take a ABC in the general linear group, then we have that A, B, C, the ijth element of that is just the sum over k equals 1 to n. of A I K B C K J, which is the sum from K is equal to 1 to N of the sum of L is equal to 1 to N of AIK BKL CLJ. But then we can do the sum in the other order, and so that's the sum L equals 1 to N of AB IL CLJ, which is AB C IJ. Okay, so we've got an associative thing, so the general linear group is a group. Okay, then we also have that the determinant det A B is equal to det A det B. That's a property of the determinant that you can learn in linear algebra, and so that means that first of all we have that det A is equal to 1 if A is in the special linear group, and the determinant of the identity is equal to 1. So therefore the determinant of A inverse is just 1 over the determinant of A. And so for all A, B in SL and F, det of AB inverse is det of A times the inverse of det of B, which is 1. Okay, so that's closed. Okay, then we have that, scribble that out for now. Okay, for all A, B in the orthogonal group N, F, we have that A, B transpose is equal to B transpose A transpose. Therefore, AB transpose AB is equal to B transpose A transpose A B, but then because they're in the orthogonal group, this must then be the identity, because obviously the two A's cancel and then the two B's cancel. Okay, so the orthogonal group is a subgroup and so on. Okay, then if we go back, we can see sort of, if we look at it, that the integers modulo n and the cyclic group sort of look the same. You know, we're basically doing the same thing to each, and so we get that a lot in maths, where we find different groups and then we find that actually they're sort of the same thing. Okay, so what we need is the idea of a homomorphism that allows us to move between groups and check how similar they are. Okay, so a map F from G to H, not F, a map phi from G to H of groups, we'll call them G with a dot and H with a times, is a homomorphism. So this means it's a sort of same morphism. If for all Fg in G, then we must have that phi of F dot G is equal to phi of F times phi of G. Okay, so that's a homomorphism. It's sort of basically what it's doing is it's preserving the multiplicative structure of the group. And so this means things like for all G in G, phi of G is equal to phi of the identity on G dotted with G, which is equal to phi of the identity of G, whatever that maps to, times phi of G, and therefore phi of the identity of G must equal the identity of H. We can sort of strip off these by multiplying by whatever the inverse of phi of G is. But we also have that phi of so EH is equal to phi of EG, but we can rewrite EG as G inverse dot G. So E of H is then phi of G inverse times phi of G, and therefore the mapping of the inverse of G is the inverse of the mapping of G. Okay, so those are some useful properties of homomorphisms. Okay, so if we go up here, we then have that, so a function phi from G to H is invertible if there exists a phi inverse function from H to G such that phi inverse of phi is equal to the identity on G, and phi of phi inverse is equal to the identity of H. Okay, so that's what an invertible function means. And so we have that phi inverse exists if and only if phi is a bijection. Okay, so a bijection is an injection, so it's injective and it's surjective. So injective means for every f and g in G, phi of f is equal to phi of g if and only if, we'll do it with an arrow, f is equal to g. So we don't get two different things map into the same thing. We're not squishing g into h, we're sort of applying g to h. And so an injection is very much you're sort of inserting g into h in a sort of faithful way. Okay. Another word for this is a monomorphism, or a one-to-one mapping. Okay. Monomorphism. Okay, and then surjective means that it also covers H, so there's nowhere in H that you can't reach with phi. So for all H in H, there exists a G in G such that H is just the mapping of G. Okay, and so that gives us, so we could also call these onto mappings or epimorphisms. Okay, so thus phi bijective means that for every H in H there exists a unique G in G, because obviously there is some G in G, but it has to be unique using this condition such that H is phi of G, and so we simply define phi inverse of H to be equal to G. Okay, and that's an inverse map. You can check that this does indeed undo it. Okay, and so a homomorphism phi from G to H is an isomorphism if and only if phi is invertible or phi is bijective. Okay, so first of all, isomorphism means sort of they're the same group. We can map the elements one to one in a way that preserves the multiplication, and we can just move between these groups freely, and any important property is preserved by this map. Okay, and we write this as G is isomorphic to H with this symbol of sort of a equals with a tilde because it's effectively the same. Okay, and so normally when we have this sort of map, we require that phi is bijective and also phi inverse is homomorphism. But with groups, we're sort of already guaranteed that because for rule G, H in H, we have that phi inverse of G times by H is phi inverse of, so we can rewrite G as phi of phi inverse of G times phi of phi inverse of H. But then we can use phi being a homomorphism to combine these two. So that's now phi inverse of phi inverse of G times phi inverse of H. But phi and phi inverse, like that composed as this, is the identity on G, so we can just remove it, and that is then phi inverse on G crossed, that should be dotted, whoops, dot phi inverse of H. Okay, so phi inverse is automatically a homomorphism, and so isomorphisms are very important. And we can see that if we go back to our groups over here, that, undo that, didn't work. Okay, we see that quite clearly if we just map k or whatever to a to the k, that is clearly an isomorphism. Okay, I think that about finishes what I want to do here. We'll get into some more sort of meaty theorems next time.